Hello, this is Byte of Code, and in this episode, we're going to be implementing the interrupt and move instructions. So in the last one, we got a lot of groundwork, and we got two small instructions, but they're really small, so you didn't really have to think about the instruction format. And basically what that is how all the instructions are going to follow the same convention, so you can, make instructions and make inline programs and whatnot. I already made some format codes beforehand to make things easier for this episode, but you can actually make your own, and that's the joy of doing it emulated. You can do pretty much whatever you want. Now with this, I just labeled all of the registers we made in the last episode from 0 to F, so there's not much here. And then in the addressing modes, I only had 2. There are hundreds that you could make, but I'm just going to start with these 2. Let's say you have a few memory addresses. The first one would be the opcode, as we can see here, so it's 1 byte. Then we have the mode, which is what mod is, and that's the addressing mode. So I could put addressing mode register immediate 8, and basically what this denotes is that the next byte in memory would be the register code, and then the one after that is the immediate 8-bit value. So let's have an example. If you want to set EAX to, let's say, 66, then we would put move address register immediate 8, 0, because that is what the EAX addressing code is, and then we would put the raw value, so 66, and this next one would be the next instruction. So this is how you denote this. Now let's say you wanted this to be a much larger value, let's say 0x 1000. Then you'd have to do register immediate 16, because this is a 16-bit value. So again, you'd go 00 because we're addressing the EAX code, and then you do 0x10, and the next one you do 00. So what this is doing under the hood is it's reading a byte, so 0x10, and then it's shifting it over 8 bits, and then it's ORing it with the next byte in memory. And that's how we get this value. So the biggest value comes first, and then the littlest come after that. This is called big endian, where the biggest value comes first. You could do little endian, where the same thing would be denoted as this, but it's a little less intuitive, so for this series, I'm going to be using big endian. And as I was showing with the example, we just have the opcode, the mode, and then register immediate, and then register or memory. This is also register and memory. So for example, with the opcode, that would be the first byte, and then the addressing mode, and then the register or memory, and this means the register code or memory. So the next byte, so it would be 1, is 0, and then the next one could be 1, 2, or 4 bytes, or none, of course, to be the thing. So if we theoretically did register immediate 32, we could do a really big value like this. And this would be totally correct, because it can be 1, 2, or 4 bytes, and this is 4 bytes. Now that we've talked about that, we can correctly make a test that when it succeeds, it means that we're pretty much done. So I've constructed a test here, and this is what we're going to run to make sure that the thing is properly working. And this is just a replacement for unit testing, and we'll be implementing unit testing in the next episode when we have a lot more to test. But currently there's just not that much. So this is the test, and to make sure that this is actually working, at the end, after it's executed, we're going to print cpu.eax. And if you want, we can also test our debug mode. So now that debug mode is true, it should return the amount of cycles we passed in. So we have the cycles, so it should return 5 if it works correctly. So we can just print cycles, and it should equal 5. Now currently we don't have support for this instruction. So if we weren't to run this, we just get some errors. And we see we get a bunch of invalid opcodes. Now we can see it uses the correct amount of cycles, but this is because it thought every single address was an invalid opcode, because it's just skipping this and this and this and this. It's not treating these as parameters for the move opcode, the instruction, because it doesn't exist yet. So let's implement it. So in here we can easily implement this. We can just add to our elif statement and check for the move instruction. Now as we predetermined, the mode is going to be the next byte. So we can reuse our fetch byte instruction again to get that. And if you don't know, the 2 underscores just means it's a private method. The next thing we need to do is have another if statement depending on what the mode is, because we're going to need to do a different thing on each addressing mode. And you can see this doesn't bring up an error, because in the int codes, I've already put these all in here. So you can copy these down. I've just put the codes for EAX, EBX, ECX, and EDX, and then the reg immediate 8 and reg immediate 16. Now what are we going to do if we get reg immediate 8 as the addressing mode? The first thing we're going to do is get the register code, which should be 1 byte, and then we're going to get the immediate value, which should be another byte. So we can again reuse the fetch byte instruction. Now what we do want to do with the move instruction from here is write to whatever the code here is. And in our example, we're doing EAX, which is 0. So if this is 0, we want to write to EAX, this value. But we should probably create a function to do that so we can reuse it over and over again. Up here, I'm just going to make another function called write register. And it's going to take in a code and a value. And it's not going to return anything. Now the easiest way to do this that I've come up with is just have another if statement depending on what the code is. So we just created this here and it's really simple. It just depends on each one, and I'm only testing for the first 4 here because these are the only ones we're going to be using. And later on we'll put the rest of the registers in this. Now we don't need to forget that since we're writing a register, we need to consume another clock cycle. And as we said right here, this isn't going to return anything. So this is all we're going to need for this function. Then we can call it. So this should be all we need to do for the move instruction. It's a really large instruction, but once you get down into it, each part of it is really simple. So let's run this and see what happens. And you can see here that it does exactly what we want it to. It used the correct amount of cycles without getting any errors, and 42 is loaded into the EAX register. So that's really simple, and doing the next addressing mode should be just as easy. But here's the thing we have to add. We need to add a fetch word. And again, this isn't going to take anything in, and it's going to return an int. And I'll just put this right next to our fetch byte instruction, so it's clear that they're related. So this function is actually really easy, because we can just call the fetch byte twice, or the results together, and then return it. You need to make sure that you shift this one 8 places to the left, because it is more significant by 8 bits. So now I can just call this as the value. So let's test this feature. Let's do reg immediate 16 instead. We'll go to do AX as well, and we'll do 0x10. And then 0xcc. And the reason that I'm using hex here is because it happens to turn out that if you shift this value 8 places to the left, it's going to equal 10 with just an extra 2 places. So it's really easy to tell if it works or not. But then to make sure it does work, let's just print the hex of cpu.eax. Let's test this out. And you can see this works perfectly. So the next thing we're going to do is we're going to be implementing the interrupt instruction. And this is going to take a lot more work because we're going to need to make an entire interrupt handling system for our CPU. But let's make a test. So let's just try 0x1. And this should only require 2 cycles because we aren't writing anything else, and we're only reading these 2 from memory. And we don't need to, well, we'll continue to print the cycles, but we shouldn't need to print EAX. Now let's go in here. And this isn't going to have any addressing modes, because all we're going to need to do is read the next byte from memory and use that as like an interrupt code. So now that we have the interrupt code, we should probably just make a handle interrupt function. So I'll put this right here. And it's not going to return anything. And we actually aren't going to do it like this, because I just realized if we want to have external interrupts, we need a way to trigger it somehow, because these are all going to be private methods. So let's define an int location. And since this is at F1, we'll just make it FO. And I'm going to make this a CPU variable. It's only used for the CPU, but I'm not going to define it in the init, so you can just call cpu.intLocation without creating an instance. Now I'm actually making this a variable, so one, we can call it externally, and so we can change it if we need. So now let's just do something depending on this location, so we won't actually need to take in any variables. And then we'll have the int code, and I haven't defined those yet, so I'm just going to leave this blank. But down here, let's actually take the int code and place it in memory. So then we don't need to pass this in. And this should work the exact same. So now let's create some interrupt codes. I'm going to do them in the same location over here, right before the init. I've already made a few. Syscall is one, and this is going to be a really important one. I'm going to follow the x86 convention of 80. I'm also going to find COM0 here, just so we don't have to define it later, and it's going to be 0xFO1, like we defined here. And then I want to make a couple more specific interrupts that we can trigger. So down here, instead of just printing a message, I want to have like a raise interrupt function. So let's create an invalid opcode interrupt. And this happens to be 6 in the x86. Now the x86 doesn't have an interrupt called out of memory because it uses more technical terms, but I want to do something very simple to understand, so I'm just going to define my own at 16, which the x86 doesn't define anything there, so we won't override any other ones that we might want to implement later. And then let's have a reserved, just so we don't accidentally define it later, and I'm going to make this 0, 0. And the reason I'm doing this is because the int code is 0, 0. So if you have nothing in memory, it's going to think it's the int instruction. So I'm just going to put 0, 0 in the int location, so then it will do nothing. But technically you don't need to have this here because you're never calling it. I'm just putting it here to denote that you should not set this as anything. So now let's do something depending on those. So if it equals self.syscall, we're going to want a separate function just to handle syscalls because it's really big and there's hundreds of syscalls that you could choose from. But we don't want to forget that we should set in interrupt to true. And we want to set the processor status interrupt acknowledged flag to off because we've already acknowledged it. So we want to say it's off so then other ones can be new instances and we'll register them as new interrupts. But before we make the handle syscalls function, I'll just put the rest of them in here. And since the rest of them aren't special and they don't require any parameters or anything, and they're basically just interrupts that you raise, they can all go to a different function, like raise interrupt or something, because they're all very similar. Syscalls are significantly different than the rest of them. And here we could do an else, or we could just have a list with all of them. But to make it a lot simpler, let's just do an else for now. And later we can make it a little more robust if we want. And then we're going to pass in what is at this location because we're doing else, so we aren't checking on it. We'll just pass the value into a raise interrupt function, and then this will do all the heavy lifting. So let's make a raise interrupt function. So this isn't going to return anything. It's going to take a code, and then it's going to take keyword args. And the reason it's going to do this is because for some specific ones, we're going to need more than just a code. Like for invalid opcode, we're going to want to know what the invalid opcode was. So we would pass in an instruction. Now we're going to wrap this all in a try catch. And the reason we're going to do that is because there's one specific interrupt that needs that data, the double fault interrupt. This is basically when there's an exception when you're trying to handle an exception. So now that we have all this set up, let's start with this section. We're going to start by having a base string that all of them will print initially to show that if you are using multiple components, it's specifically coming from a CPU interrupt. And then the rest of them will just append to the string depending on what the interrupt is. So now let's go depending on what these are. So let's start with invalid opcode. For invalid opcode, we're going to append to the string. And then here's where we're going to use the keyword args. First, we're going to pass in the hex of the keyword arg, and we're probably going to call this opcode. And then we'll put the program counter, and we don't need to pass this in because it's a class variable. Now let's do our other one. This one doesn't need anything else. All it needs is the program counter, so we don't need to pass in any keyword args for this one. And then here's where the double fault comes in. First, let's make a double fault. And this is 8. And then back down here, we can catch any exception. And then we can pass in this into a double fault exception. And the reason I'm doing this in a debug is just so it prints it. But normally, if we aren't doing debug, we're actually just going to raise an exception. And the message is going to be a little different. It's just going to append to the string. So this will actually tell you in what step it happened. If it happened right here, the string would be nothing. If it happened right here, the string would be CPU interrupt. And if it happens right here, you would actually get the message plus double fault. So it gives you a little more info. And since we're raising an exception here, if it does manage to fail, it will exit the function. So now we're going to raise the exception that we want to raise, which would be the interrupt. So you're just going to pass in string for this. So we get a CPU interrupt, and this is actually exactly what we expected, because we haven't implemented any interrupt that has 0x1 code. So now let's try raising an exception that does exist. And here we get a CPU interrupt, double fault 0x2. And the reason this happened is because an opcode was not passed in. So to fix that, we can just do a if keyword args. And that's the good thing about testing. If there's any errors, you'll find them. And now we can see we get interrupt invalid opcode unknown at address 0x2. So now if we try something that doesn't require keyword arg, so out of memory, which is our only other one, and we try this, then we get out of memory 0x2, which is the current program counter that we are at. And the reason that I'm incrementing it by 1 is because if we truly are to memory, then we want to print out the address that doesn't exist, not the current address. So normally when this is getting raised automatically, it would make sense, but since we're purposely raising it, it just is a little weird. So before we go into syscalls, I want to implement a few more interrupts that are going to be really useful. And these are single step interrupt and breakpoint. And the codes for these are 1 and 3. So what these are is single step interrupt is if the trap flag is enabled, whenever an instruction is found, it will just call this. So every time a new instruction is invoked. The breakpoint is one that you invoke purposely in the memory by using a reserved instruction code. And this code in the x86 is CC. And we'll also be using CC. So we're going to do single step interrupt, and then we're just going to put the memory address that we are currently at. But since this is a single step interrupt and it's going to mainly be used for the trap flag, we want a way to make sure the person acknowledges. So we're just going to do an input with the string, and then we'll just return. Now the next one's the exact same, so we can actually just copy this, but we'll just change this to breakpoint. And the reason it's the exact same is because it does the same purpose, but it's separate interrupts. The breakpoint, you have to do each individual breakpoint, and this is every instruction by the trap flag. Now let's go implement these two interrupts, and then we'll go into syscalls. And what I mean by implement is put them in how they'd be used. So if the instruction equals CC, then we're just going to raise an interrupt, and it's going to be a breakpoint. And then the trap flag is just if the trap flag's set, then we're going to raise a single step interrupt. So now these two are implemented. So let's go test them. First, we'll start out by doing the CC, and we'll just do 2 of them. And then we can actually test both of them at the same time. So if you just change the processor status T to 1, so we've got a single step, a break, a single step, and then a break, and use 2 cycles. So that's perfect, but I do want to change one thing. We need to decrement the program counter for the breakpoint. There's no reason to do it for the single step because you're doing it before you fetch the instruction. But we want to decrement it for this because we're actually using a cycle to check if there is a breakpoint. And so we'll subtract 1. It's a super easy fix. So if you were to run this again, it'd make a little more sense. So now let's handle syscalls. So I have a ASM here that I made with just some quick syntax highlighting that I set up in VS Code using just a settings.json and then a local extension. And you can see all the conventions I made here with all the syntax highlighting, and here's all the instructions we're going to be using. So at the start here, how this syscall would work, we move into AAX, we move into EAX the write syscall, which is 4. And then to EBX we'll write where this is outputting to, and 1 happens to be standard out, which is what we want. ECX is the start location of the message, so we just pass in a pointer to the message, and this is how I'm going to choose to do it syntactically. So this would just point to wherever this is. And then EDX is the length of the message. So we can just do message len. So in assembly, this is how you'd normally do it. But since we're doing an inline program, what we're actually going to do is just count it out to make it super simple. So it would be 13. And then we use the INT instruction to call the syscall. And if we were to run this, which I don't have language support defined for this, it would move 4 into EAX, 1 into EBX, the pointer into ECX, and the length, not the pointer to the length, so this would be a const actually, into EDX. and then you'd call the syscall, and the result would basically be something like this. So it just print hello world to the terminal. So first let's make an inline program in following this. So first let's start with the data, and I'll just make this at 0x100. It doesn't really matter what this is. And to make it easy to know what the binary value for is, I'm going to use the ord function. We'll take the Unicode ordination of the binary of the character you put in. And I'm just going to copy and paste this to make it a lot easier. So here's our message, starting at 100, going into 10C. It's going to be hello world. Then we're going to make this program, and this is going to start at 00. So we're going to start with the MOV instruction. And then we can do the address of immediate 8, because we're putting in 4, which is an 8-bit value. We're going to pass in EAX. And then we're going to pass in the value 4. So you can see I skipped an address here, and this is because the pointer to the location is actually a 16-bit value. So now we're going to use that reg immediate 16 on ECX, and then we'll do the first two, which would be 01, and then the next address would be 00. So technically we don't need to set this because it's default to 00, but I'm going to do this to indicate that we're doing an address. And then finally after this, we're just going to call an interrupt. So this is going to take 23 cycles if I counted correctly. This is because it's going to be 2 for the interrupt. And then it's going to be 5 for each of these move instructions. But it's going to be 6 for this one because we're reading 2 bytes from memory here. So if we run this program, we can see it just prints out this amount of cycles. So at least we aren't getting any errors. And to make sure that our move instructions are working correctly, at the end, we will just print the hex of EAX through EDX. So now if we run this, we get 4, 1, 100, and D. And this is exactly what we wanted, because the message length here is 13, which happens to turn out to be D. So even though we're only going to be implementing write in this episode, I do want to get out around 8 here to begin with, so then we won't need to come back and redefine a lot more later. So restart syscall. And this one's a little weird, so I'm going to separate that a little. So we have sysexit, which is 1, and all this does is exit the program. Sysfork, which forks, obviously. We have sysread, which just gets an input, like the input command in Python. So in the reality, in the x86, whenever you're doing a break command, if we were implementing this like a real x86, we wouldn't actually just do input, but if we were, it'd be more accurate if we'd call our own sysread. But since that's a lot more complex and there's really no reason to do that, we aren't going to do that. Then we have syswrite, which is the one we're going to be implementing, and this is 4. Then we have open, which just opens a file and puts it into RAM. This closes the file, so it just takes it out of RAM. This gets the current time from the epoch as an integer. And I couldn't get good documentation on what ftime did, but I'm just going to assume it gets the time as a double precision float using the IEEE format. So that's how I'm going to be implementing it. If that's not actually how it goes in the real x86, please let me know. And the last one we're going to write down here is syscreate, which is 8. And this just creates a new file. So when they handle syscalls, instead of looking at a certain memory address and doing something based on what that is, we're actually going to do something depending on what's in the EAX register. And as you saw here, we're loading what the syscall is into the EAX register. So if self.eax equals syswrite, then we're going to do something depending on what that is. Now we're just going to have another if statement, and this is going to be if ebx equals 1. And this is because 1 indicates that it's standard out, and we probably won't have any else condition for this because we're mainly just going to be dealing with the terminal. But maybe if we do get pretty advanced and get our own window to the screen, then eventually we might use something else here. So the way I've decided to do this is pretty simple. All you're going to do is have a string, and then you're going to go through memory until you reach the limit, which is at edx, and then you're going to stop, and then you're going to print that string. So we're going to need a string, a counter, and since there's no do-while loops in Python, we're just going to initialize our character first. So we're going to get the location of ECX, because we're loading in a pointer here, not the actual value, because of course it's an ASCII string, so we couldn't load in the value. So it's just going to be a pointer, and the start character is going to be where we loaded it into. And then we're going to have while counter is left in EDX. And if it is, you're going to append the character of car, and this is because this is going to be a integer value, not the actual character, because we're loading in the ordination of it. So we're going to need to use the character function on that. Then you're going to increment the counter, and then you're going to reinitialize what the character is. And this is going to be self.ex plus counter. So now that we have our entire string, we're going to do something depending on if it's debug or not. If it is debug, we're just going to show what the interrupt is instead of just printing it to the screen. So it's going to be something similar to our other interrupts. So I have a lot more info. We have interrupt, syscall, write, standard out. And this is because if we're in debug mode and it wasn't standard out, we'd still want to show that there is an interrupt, but we'd still want to show where it's happening. But this is the only one where it'd actually print the string directly afterwards. And then if it's not in debug mode, we're just going to print the string. And make sure to make the end nothing, because in Python it will default to new line, but in reality that's not what we want, because usually in a assembly program you'd either see an A, which is the new line, or you just see a new line in here, which is only supported sometimes. And we're obviously going to support this, but since if we do want to have a new line character here, we don't want there to be two new lines. Now, one thing I forgot about is that this is going to take significantly more than 23 cycles, and that's because it's reading from memory a lot. So what we're going to do here is decrement cycles initially, and then each time the loop comes around, we'll decrement it again. So to fix this, all we need to do is move these two lines of code from the bottom to the top of the function, and then strip out the initializer for the character up here, and then it should consume the right amount of cycles. So if you don't subtract this value and we run this program again, it should result in 36. And you can see it gets through 36 cycles, which is what we wanted, and it still prints the entire message. So let's try this without debug mode to make sure it's still working. And you can see this is perfect. Now you can see my terminal is a little messed up. And to make sure this doesn't happen, we probably just want to print a new line at the end of our function. So I'll just do it right here. And now my terminal is not broken, which is great. that's the end of this episode. We got a lot of progress by implementing the move instruction and interrupt instruction, and we implemented a syscall, which is really cool. In the next episode, we're going to be adding some more syscalls and a few more instructions to prepare ourselves for the episode after that, when hopefully we'll start making a calculator app.